Welcome back to Bite-Sized Breakthroughs, where we unpack cutting-edge research in the world of AI and deep learning. Today, we're diving into a fascinating paper that tackles the ever-present challenge of computational efficiency in deep neural networks. Joining me is Dr. Paige Turner, the lead researcher on this project, and Professor Wid Spectrum, a leading expert in the field of network compression. Welcome to both of you.
Thank you, Alex. It's great to be here. It's a pleasure to join you, Alex.
Dr. Turner, let's start with the basics. Could you give us a brief overview of the problem addressed in this paper? Why is computational efficiency so crucial in deep learning?
Absolutely, Alex. Deep neural networks, while incredibly powerful, are often computationally intensive and require a lot of memory. This makes them challenging to deploy on resource-constrained devices, like mobile phones or embedded systems, and limits their application in real-time tasks that require rapid processing. Take, for example, the VGG16 model, a popular architecture for image recognition. It has over 138 million parameters and requires over 30 billion floating-point operations, or flops, to process a single image. That's a lot of processing power for even a powerful computer, let alone a smartphone.
So we need to find ways to make these models more efficient without sacrificing their accuracy. That's where network pruning comes in, right?
Exactly. Network pruning is a model compression technique that aims to reduce the complexity of a deep neural network by removing unnecessary components. We can do this by identifying less important connections, filters, or even entire layers and discarding them. This leads to a smaller model with a reduced number of operations, making it faster and more efficient.
Professor Spectrum, could you elaborate on the historical context of network pruning? Where does this research fit in the broader landscape?
Network pruning has been around for a while, Alex. It's a classic method for reducing model complexity, dating back to the early days of neural networks. The idea is quite intuitive. If certain parts of a network aren't contributing significantly to the final output, why keep them? The challenge lies in identifying which parts are truly unnecessary without harming the model's performance. Early work focused on pruning connections based on the magnitude of their weights. However, this often led to irregular network structures that hindered actual inference speed. More recent research has focused on structured pruning, like filter-level pruning, which removes entire filters at a time, preserving the original network structure.
So, Dr. Turner, what are the key innovations in this paper? What makes AutoPruner different from previous approaches?
That's where AutoPruner comes in, Alex. Most previous filter pruning methods have followed a three-stage pipeline. They first train a model, then identify and prune less important filters using a heuristic method, and finally, fine-tune the pruned model to recover its accuracy. This approach has several limitations. First, it's difficult to find a perfect criterion for filter importance that works well across all networks and tasks. Second, pruning and training are treated as separate steps, hindering their potential synergy. AutoPruner addresses these limitations by integrating filter selection directly into the model training process, making it an end-to-end trainable method.
That's quite an interesting shift. How does AutoPruner actually work? Can you walk us through the methodology?
AutoPruner introduces a novel channel selection layer that functions as an independent layer within the network. This layer receives activation responses from a previous convolutional layer and generates a binary index code. Each element in this code represents a filter in the previous layer, with a 1 indicating that the filter should be kept and a 0 indicating it should be pruned. The magic happens during training. The channel selection layer is trained alongside the rest of the network, ensuring that the model learns to select filters that optimize both accuracy and sparsity. This allows for automatic filter pruning during the training process, eliminating the need for separate pruning steps. During training, the model gradually erases filters with a binary index code of 0, further refining the model by focusing on the preserved filters and their connections.
That sounds incredibly efficient. But how do you ensure that the binary index code is consistent across different input batches, leading to accurate pruning? I imagine that inconsistencies could lead to issues where some filters are pruned in one batch but retained in another.
That's a great point, Alex. To address that, AutoPruner incorporates two key elements. Mini-batch pooling and binarization. Mini-batch pooling aggregates information across different images in a batch to ensure that the binary index code is consistent across all samples. This is done by averaging the activation responses of each filter across all images in the batch, making the code more robust to variations in individual examples. Then, the binarization process, which uses a scaled sigmoid function, gradually forces the output of the channel selection layer to become binary, 0 or 1, making it clear which filters should be pruned. This gradual binarization allows the network to progressively discard unimportant filters while enhancing the influence of preserved filters.
So, the network learns to make a clear decision about which filters to prune, and this decision is consistent across different batches. Professor Spectrum, can you provide any insight into how this methodology compares to existing approaches?
AutoPruner's end-to-end trainable approach is a significant departure from previous three-stage methods, Alex. This integration of filter selection and fine-tuning allows for a much more natural and efficient optimization process. It's akin to teaching the model to learn not just the weights, but also the structure of the network itself. Furthermore, the gradient information flowing from the channel selection layer helps guide the training of previous convolutional layers, resulting in improved accuracy compared to methods that treat pruning and fine-tuning as separate steps. Prior methods, like ThigNet, used heuristics based on the statistics of the next layer to determine filter importance. While effective, this approach was not as adaptive or as efficient as AutoPruner. Similarly, SSS used scaling factors to indicate filter importance, but it lacked the ability to use pruning information to influence the training of previous layers, leading to lower accuracy.
That's a very insightful comparison. Dr. Turner, can you tell us about the experimental setup? What datasets did you use to evaluate AutoPruner's performance, and what metrics were employed?
We evaluated AutoPruner on two standard datasets, CUB200-2011, a fine-grained bird recognition dataset, and ImageNet ILSVRC-12, a large-scale image recognition dataset. We chose these datasets because they represent challenging tasks with diverse image types and complexities. We also used two popular deep learning models, VGG16 and ResNet50. We used the PyTorch framework and conducted the experiments on M40 GPUs. To evaluate performance, we used standard metrics like top 1 accuracy, top 5 accuracy, and the number of floating point operations, flops, required for inference. We also calculated a theoretical speedup ratio based on the reduction in flops.
Dr. Turner, can you share some of the key findings from your experiments? What were the most significant results?
AutoPruner consistently outperformed state-of-the-art filter pruning methods on both datasets. On CUB200-2011, AutoPruner significantly surpassed ThigNet and random selection in terms of top 1 accuracy for various compression ratios. For instance, with a compression ratio of 0.5, AutoPruner achieved a top 1 accuracy of 73.45%, while ThigNet reached 73.0%. This advantage was even more pronounced with a smaller compression ratio of 0.2, where AutoPruner achieved 65.06% top 1 accuracy compared to ThigNet's 63.12%. On ImageNet, AutoPruner exhibited superior accuracy compared to SSS, RNP, channel pruning, and Taylor expansion, especially for higher compression ratios. For example, on the VGG16 model, AutoPruner achieved 69.20% top 1 accuracy with a compression ratio of 0.4, while SSS reached 68.53% with a similar compression ratio. AutoPruner also demonstrated advantages over ThigNet on ResNet50, particularly when pruning multiple layers simultaneously. With a compression ratio of 0.3, AutoPruner achieved 73.05% top 1 accuracy, surpassing ThigNet's 68.42% with a similar compression ratio.
That's incredibly impressive. Those results clearly show that AutoPruner is a powerful tool for compressing deep networks without sacrificing accuracy. However, every method has its limitations. What are some of the key limitations of AutoPruner, and what directions do you see for future research?
While AutoPruner shows significant promise, Alex, there are areas for improvement. The current study focuses primarily on image classification tasks, and its effectiveness in other vision tasks, such as object detection or semantic segmentation, remains to be explored. We also haven't investigated the performance of AutoPruner with different hardware architectures or optimized hardware implementations for sparse networks. Further research is needed to understand the practical implications of the method in real-world scenarios. Additionally, the hyperparameter tuning process, particularly for AuStart, may require some experimentation to find optimal values for different network architectures and tasks. Looking ahead, we plan to explore the performance of AutoPruner in other vision tasks, investigate its performance with various hardware architectures, and develop more sophisticated methods for adaptive compression ratio control based on dynamic task requirements or resource constraints.
Professor Spectrum, from a broader perspective, what are the potential applications and impacts of this research? How could AutoPruner change the landscape of deep learning?
AutoPruner has the potential to significantly impact the field of deep learning, Alex. Its ability to efficiently prune deep networks without sacrificing accuracy could enable the deployment of complex models on resource-constrained devices like mobile phones, making powerful AI capabilities accessible to a wider range of applications. This could lead to breakthroughs in areas like mobile vision, augmented reality, and robotics, where computationally expensive models were previously impractical. Furthermore, AutoPruner's success could encourage further research into end-to-end trainable approaches for other deep learning tasks, potentially leading to more efficient and robust models across the board. Its potential applications are vast, extending beyond image classification to other areas like natural language processing, object detection and tracking, medical image analysis, and speech recognition. By making deep learning more accessible and efficient, AutoPruner could contribute to a more intelligent and interconnected world.
That's a very optimistic outlook, Prof. Spectrum. To wrap up, Dr. Turner, could you summarize the main takeaways from this research? What are the key insights we should keep in mind?
This research demonstrates the potential of end-to-end trainable methods for filter pruning in deep neural networks. AutoPruner's ability to automatically select filters during training without requiring separate pruning steps leads to significant improvements in accuracy and compression ratio. The combination of mini-batch pooling and binarization operations plays a crucial role in ensuring consistent and accurate pruning. Furthermore, AutoPruner surpasses training from scratch for similar model complexities, highlighting the value of pruning for achieving efficient and accurate models. These findings could lead to a new era of more efficient and accessible deep learning models, expanding their reach across various applications and driving advancements in AI research.
Thank you both for this incredibly insightful conversation. It's clear that AutoPruner represents a significant step forward in the field of network compression. We've learned about its innovative methodology, the compelling experimental results, and the exciting potential implications for the future of deep learning. Listeners, be sure to check out the full paper, linked in the show notes, to delve deeper into the technical details. And join us next time for another bite-sized breakthrough.